We now turn our attention to conservative vector fields. So we say that a vector field f is a conservative vector field if there is a scalar function f, little f, such that f is del f, right? So a vector field is conservative if it is the gradient of some scalar function. And we call the scalar function as f the potential function of the vector field. Now, conservative vector fields do play a very important role in physics, and we will see some conservative vector fields in physics at the end of this video. Suppose that we have a conservative vector field, and let's suppose that we have two potential functions for it. Call them f1 and f2. Now, the gradient of f1 minus f2 is the gradient of f1 minus the gradient of f2, but since both are potential functions for the vector field f, that just becomes f minus f, which is the zero function. This would mean that f1 minus f2 is a constant. So f1 is f2 plus a constant. Now what this says is that conservative vector fields on an open connected domain have unique potential functions up to a constant. That is, if you have any two potential functions of a conservative vector field, they differ only by a constant. So now that we know what a conservative vector field is, how can we determine whether a vector field is conservative? Right? So let's consider the conservative vector field f. Then there would be a function f such that f is the gradient of little f, that is, the vector field is partial f partial x, partial f partial y, partial f partial z. What this means is that f1 is equal to partial f partial x, f2 is partial f partial y, f3 is partial f partial z. We will now go ahead and calculate all mixed partials. And here they are. So partial f1 partial y is this, partial f1 partial z is this, so on and so forth. However, the order of the mixed partials do not matter, right? Remember that? So, in other words, this one here would equal this here, right? So we have partial f1 partial x and partial f2 partial f1 partial y and partial f2 partial x would have to be equal. We have partial x partial z here, partial z partial x there. These would have to be equal. So partial f3 partial x and partial f1 partial z would have to be equal. And finally, here we have partial z partial y, here we have partial y partial z. So partial f2 partial z and partial f3 partial y are equal. And that is summarized here. Now we call these the cross partial equations, and each derivative a cross partial derivative, or simply the cross partial. Thus, if f is conservative, then the cross partials are equal. And in fact, we can say that f is conservative if and only if the cross partials are equal. We offer this second part of the proof, that is, we offer the direction if the cross partials are equal, then f is conservative, without proof, since we do not yet have all the tools required to prove it. So we've proven the one direction, right? We've proven if f is conservative, then the cross partials are equal. The other direction is often without proof, and so we can write it as an if and only if statement. If we now take a look at the curl of a conservative vector field, then this is what we get. However, as we just saw, all these cross partials are going to be equal, and so the curl of a conservative vector field is 0. And again, in fact, this is an if and only if statement. Right? So here we've just shown that if f is conservative, its curl is 0. Again, offer without proof. If the curl is 0, then it's conservative. It's a conservative vector field. So a vector field is conservative if and only if its curl is 0. Alright, so here we're asked to determine whether this vector field is conservative, and if it is, to find a potential function for it. So there are two ways to go about determining if it's conservative. We can either calculate the curl, or calculate the mixed part, the cross partials, and see if they're equal. So here we're just going to go with the curl. So del cross f. So we're going to have 1 minus x squared over z squared minus 1 minus x squared over z squared. Then have negative 2xy over z squared plus 2xy over z squared. And we will have 2x over z minus 2x over z. And this is indeed 0, 0, 0. So f is conservative. We just now have to find a potential function for it. Well, this is fairly simple to do. Remember, we're looking for a function f such that partial f partial x is equal to f1, so in this case equal to 2xy over z. Partial f partial y must be equal to z plus x squared over z. And partial f partial z has to be equal to y minus x squared y all over z squared. So f of x, y, z, what we do is take any one of these three and integrate. Now the easiest one to integrate here would be this one. Right? If we integrate this with respect to y, there are no y's here. It's really easy. So that's what we're going to do. Okay, so this is just z plus x squared over z times y. Now we have a constant function, but remember it has to be constant with respect to y. Well, if we differentiate a function of just x and z with respect to y, we get 0. It behaves as a constant function. However, this can't stand. We now need to determine what this g is. Well, to do that, we make use of one of these other two. So we can differentiate this either with respect to x or with respect to z. Let's go ahead and differentiate with respect to x. We'll get 2xy over z plus g sub x of x and z. But this had to equal this term right here, 2xy over z. Thus, we can conclude that g sub x of xz is 0, which means that g of xz is actually just some function of z, right? If you differentiate a function only of z with respect to x, you get 0. So we have now is f of x, y, z is equal to z plus x squared over z all times y, plus now just a function of z. But again, this can't stand. We have to determine what this h of z is. And to do this, we take the partial with respect to z. We'll get 1 minus x squared over z all times y, which equals y minus x squared y over z. I'm sorry, it's plus h prime of z. All right, so this is y minus x squared y over z plus h prime of z, but this had to equal this partial partial. So that had to equal y minus x squared y over z squared. This means that h prime of z is equal to 0, which means that h of z is actually just a constant function. We now have f of x, y, z is equal to z plus x squared over z all times y plus a constant. Now we can set our constant to be whatever we want. So we can set it to be 0, for instance. And we can get a potential function f as simply zy plus x squared y all over z. You don't have to set the constant to 0. You can set it to any value you'd like. And again, the easiest value to set it to is just 0. And so that's what we'll do. All right, let's look at a special type of conservative field known as the unit radial field. So consider the radius function of a sphere, that is, r is equal to the square root of x squared plus y squared plus z squared. Then, the gradient of r is this, right? Partial partial x of this, partial partial y, partial partial z. When you do this out, you'll get x over r, y over r, z over r. Now we call this the unit radial field. Another common field, especially in physics, is the inverse square field, which is a field of the form E sub r over r squared. So it's the unit radial field over the radius squared. Now this is also conservative. So to show that it's conservative, let's assume that the potential is negative 1 over r. Now, this makes sense because the absolute value of E sub r, or the norm of E sub r rather, is 1, right? It's unit. So it makes sense just to integrate 1 over r squared dr and take that as our potential function, and that would be negative 1 over r. So if we go ahead and take the gradient of negative 1 over r, we get 1 over r squared times the gradient of r, this is chain rule, which is E sub r, right? Because remember, the gradient of r is E sub r, all over r squared. So, yes, this is conservative, and it has potential function E sub r over r squared. Oh, I'm sorry, has potential function negative 1 over r. Now, one of the most important uses of the conservative vector field is known as the fundamental theorem of line integrals. So first, we need some terminology. When a curve C is closed, we often refer to the line integral of any vector field around C as the circulation of f around C, and it'll be denoted in this manner right here. Right? It's the typical line integral symbol, but now there's a circle. When considering a closed curve, it does not matter which point we take as our starting point, right? Because we're going around the entire curve, right? So let's say this is our curve here. Since we're going to be tracing the entire path, it doesn't matter where we start, right? We could start here, for instance, and then we round the entire curve, and we have to come back to the starting point. Or we could start, let's say, up here, right? But we still have to go around the entire curve to get to the starting point. So the path that we traverse is going to be the same no matter where we start. This is only because we're dealing with a closed curve. Now here is the fundamental theorem of line integrals. Assume that f is a conservative field on a domain D. If R is a path along a curve C, from P to Q in D, then the line integral along the curve C of f dot dr is equal to f of Q minus f of P. And the circulation around C of f dot dr is 0. So let's go ahead and prove this. So let R of t be a path along the curve C in the domain D for A less than or equal to T less than or equal to B. And we're going to say that R of A is equal to P and R of B is equal to Q. Then the path integral of f dot dr is the path integral of the gradient of little f dot dr because big F is conservative, right? So this is the potential for F. Well, this is going to be the integral from A to B of the gradient of F evaluated R of t dotted with R prime. Now, b dt of f of r is the gradient of f of r dotted with R prime by integral. So, by the fundamental theorem of calculus, this integral can now be written like this. But if you take the integral of a derivative, remember they're inverses essentially, inverse operators of each other. So this is just f of r evaluated from t equals a to b. So this is f of rb minus f of r of a. But we said that r of b was q, r of a is p, so we have f of q minus f of p. So that proves the first statement. Now, if c is closed, then p is equal to q, and so f of q minus f of p is 0, and thus the circulation of f around c would be 0. That proves the second statement, and so the overall proof is completed. Now, that first result of the fundamental theorem is known as path independence because it says that the path used to integrate a conservative vector field does not matter. Right? In other words, let's say we have a really complicated looking curve. Let's say it's something like that. And we want to go, right? We want to integrate from P to Q. And we know that F is conservative. Well, what the first one says is path independent. We don't have to try and parameterize this complicated looking curve. We can just go, okay, there's our path. That's the path we'll take. Now again, it's important to note that this only holds for conservative fields, right? Only conservative fields. We will now look at some conservative fields in physics. Now recall that we have already shown that the field E sub r over r squared is conservative. So one such inverse square field is known as the gravitational field. It is F equals negative gm over r squared times E sub r. G is the gravitational constant. It is a fixed universal constant. This is approximately its value. M is the mass of the object, and r is the distance from the object. So this is the gravitational field of an object, such as the Earth. A second field is known as the electrostatic field. Q over 4 pi epsilon naught r squared times E sub r. Q is the charge of the particle. Epsilon naught is approximately 8. This value here. F is known as the unit farads. This is the permittivity of free space. Again, it is a fixed universal constant. And r is the distance from the particle. So this is the electrostatic field that a charged particle exerts. Now the convention in physics is to represent the potential function in the form of negative v. If we use this convention, then we write F is negative del v. What we're asked to do is to compute the work against Earth's gravitational field required to move a satellite of 600 kilogram mass from an orbit of altitude 2,000 kilometers to an orbit of altitude 4,000 kilometers. And we have two constants here. The mass of the Earth is 5.98 times 10 to the 24th kilograms, and the radius of the Earth is about 6.4 times 10 to the 6th meters. Now, F, we want the gravitational field. G, mass of the Earth over the radius of the Earth, over r squared rather, times E sub r, the unit radial field. To rewrite this, we can write it as negative g times mass of the Earth times the unit radial over r squared. And this has to equal negative del v. Now, recall that for an inverse square field, the potential function, I'm not going to use v, F was negative 1 over r. So for an inverse square field, or for this inverse square field, we have negative v is g mass of the Earth over r. Right? And so v itself is negative g m sub e all over r. Now, the force we have to overcome is m times f, where little m is the mass of the satellite. So the force that we have to apply is the opposite of that. Now, f is conservative, so the path we use does not matter. So work will be the path integral along some path c of negative m f dot dr, which equals m times the path integral of f dot dr. But this is m times del v dot dr. I forgot to put a negative out here, right? That's why this is positive. So by the fundamental theorem of line integrals, this is just mv evaluated from some radius r naught to a radius r sub 1. Plugging in v, we get negative g m m, I should say g m sub e m, all over r, from r naught to r1. Now what we're going to do is we're going to say, okay, r naught is the radius of Earth plus this altitude, the initial altitude, 2,000 kilometers, which is 2 times 10 to the 6th meters. And r1 would be the radius of the Earth plus the highest altitude, the final altitude, which is 4,000 kilometers, or 4 times 10 to the 6th meters. Thus, our work, negative g m all over radius of the Earth plus 4 times 10 to the 6th. Then we get plus g m all over r sub e plus 2 times 10 to the 6th. If we plug in all of our values, you'll find that this is about 5.48 times 10 to the 9 joules. So this is the work that would be required against Earth's gravity to move a satellite from an altitude, or a 600 kilo satellite, from an orbit of 2,000 kilometers to an orbit of 4,000. Now, one of the most, if not the most important result from physics is known as the principle of conservation of energy. And what it says is let E be the total energy of a particle if the particle is moving under the influence of a conservative force field, and then dE dt is equal to 0. So a particle moving a conservative force field has no change in energy. Now in this course, we will only consider the kinetic and potential energies. However, anyone who studied physics knows there's way more than just these two. So we have an electron traveling in the positive x direction with speed of 10 to the 7th meters per second. When it passes x equals 0, a horizontal electric field, E equals 100 xi hat, measured in newtons per coulomb, is turned on. We are asked to find the electron's velocity after it has traveled 2 meters. We are to assume that the charge of the electron, the raised charge of the electron to the mass of the electron, is negative 1.76 times 10 to the 11th coulomb per kilogram. Now the total energy of an electron is 1/2 mass of the electron times the square of its velocity plus the charge of the electron times its potential. By conservation of energy, we must have that 1/2 me v of 0 squared plus q times the potential at 0 equals 1/2 me times v at 2 squared plus qe times v of 2. This means that v of 2 squared is 2 over the mass of the electron times 1/2 me v of 0 squared plus QE times the potential at 0 minus QE times the potential at 2. This equals V of 0 squared plus 2 times QE over ME times V of 0 minus V of 2. This means that the velocity at 2 would be the square root V of 0 squared plus 2 QE over ME times potential at 0 minus the potential at 2. We just need to find V of x, the potential. Now, since E is conservative, we know that E is equal to negative del V. Now, the electric field, we were told, was 100 x 0, 0. Right, now this has to equal negative V sub x, negative V sub y, negative V sub z. Now, Vy and Vz are equal to each other, and they're both 0. This means that negative V sub x equals 100x, which means that negative V of x is 50x squared, which of course means that V of x is negative 50x squared. Therefore, what we find is V of 2 is the square root 10 to the 14th plus 2 QE over ME times 0 plus 200. When we simplify this and plug in the value for QE over ME, we get V of 2 is about 5.44 times 10 to the 6th meters per second. And that concludes this video, concludes our look at conservative vector fields.